While medieval Europeans struggled with Roman numerals and had no concept of zero, the ancient Maya were calculating astronomical cycles millions of days into the future. They invented zero independently around 36 BCE. They used a sophisticated base 20 number system requiring only 3 symbols, and they calculated the solar year to 365.242 days, more accurate than Europe would achieve for another 1,000 years. Today, we're revealing the mathematical genius of the Maya civilization. Before we discover the brilliance of Maya mathematics, don't forget to subscribe and turn on notifications. We're exploring ancient scientific achievements every week. Let's uncover the numbers. The Maya civilization flourished from approximately 2000 BCE to 900 CE across southern Mexico, Guatemala, Belize, and Honduras. They built magnificent cities like Tikal, Palenque, and Chichen Itza. They developed sophisticated hieroglyphic writing, and they created one of the most advanced mathematical systems in the ancient world. While Europe relied on cumbersome Roman numerals throughout the Middle Ages, the Maya had already developed concepts that wouldn't reach the Old World for centuries. Zero as both a placeholder and a number. Positional notation for representing large numbers efficiently. Advanced astronomical calculations requiring complex mathematics. Today, we're exploring how Maya mathematics worked and why it was so revolutionary for its time. The Vigesimal system. Base 20 mathematics. The Maya used a Vigesimal number system. That means base 20, instead of our base 10 decimal system. Why base 20? Almost certainly because humans have 20 digits total, 10 fingers and 10 toes. Maya children learned to count on both their fingers and toes. This created a natural base 20 system. The brilliance wasn't just the base they chose, it was how efficiently they represented numbers. The Maya required only 3 symbols for their entire number system. A dot represented 1, a bar represented 5, and a shell symbol represented 0. That's it. Just 3 symbols could express any number, no matter how large. Compare this to our system, which requires 10 different symbols, 0 through 9. Or Roman numerals, which needed 7 letters, I, V, X, L, C, D, M, and still couldn't efficiently represent large numbers. Numbers 1 through 4 were shown as dots. 1 dot, 2 dots, 3 dots, 4 dots. 5 was a horizontal bar, 6 was a bar with a dot above it, 10 was 2 bars, 15 was 3 bars, 19 was 3 bars with 4 dots, the maximum you'd see in any single position. Beyond 19, the Maya used positional notation. But unlike our system where positions move left to right, the Maya wrote vertically. The bottom position represented ones. The next position up represented 20s. The next represented 400s, 20 squared. Then 8,000s, 20 cubed, and so on. The revolutionary concept. Zero. Here's what made Maya mathematics truly advanced. The Maya invented zero independently, one of only a few cultures in world history to do so. The earliest confirmed use of the Maya zero appears on a stela at Chiapa de Corzo, dated to 36 BCE. That predates the Hindu-Arabic zero, which appeared in India around the 5th century CE, and it was over a millennium before zero reached medieval Europe. The Maya zero, represented by a shell glyph, served 2 crucial functions. First, as a placeholder. In positional notation, 0 indicates an empty position. Without it, you can't distinguish between numbers like 21 and 201. The shell in the 20s position told you that position was empty. Second, as a number in its own right. 0 represented absence, completion, the end of a cycle. This dual function required sophisticated mathematical thinking. Some ancient cultures, like the Babylonians, used placeholder symbols. But they didn't treat 0 as an actual number you could calculate with. The Maya did. This allowed them to perform complex calculations that would be impossible otherwise. Astronomical precision. Calculating the cosmos. Why did the Maya develop such advanced mathematics? The answer lies in astronomy and calendar calculations. The Maya were obsessed with tracking celestial cycles. Their religious and agricultural life depended on precise timekeeping, and this required serious mathematical capability. The Maya calculated the solar year as 365.242 days. The modern value is 365.242198 days. That's accurate to within 17 seconds per year. Medieval Europe used the Julian calendar, which calculated the year as 365.25 days. This accumulated an error of about 11 minutes per year. By the 16th century, the Julian calendar was 10 days off. The Maya system was far more accurate. They also calculated the lunar month with remarkable precision. At Copan, Maya astronomers determined that 149 lunar months lasted 4,400 days. This gives 29.5302 days per lunar month. At Palenque, they calculated 81 lunar months as 2,392 days. This gives 29.5308 days per lunar month. The modern value is 29.53059 days. The Maya got within 0.002 days of the true value, without telescopes, without modern instruments, just careful observation over centuries and sophisticated mathematical calculation. The Dresden Codex, one of only 4 surviving Maya books, contains astronomical tables. These track the synodic period of Venus, the time it takes Venus to return to the same position relative to Earth. The Maya calculated this as 584 days. The modern value is 583.92 days. They divided Venus's cycle into 4 phases: morning star appearance 236 days, disappearance behind the sun 90 days, evening star appearance 250 days, disappearance between Earth and Sun 8 days. This level of astronomical precision required complex calculations involving hundreds of millions in their numerical system. The Maya regularly worked with numbers far larger than anything medieval Europeans could manage with Roman numerals. The calendar systems, mathematical complexity. The Maya used multiple interlocking calendars, each requiring sophisticated mathematics. The Tzolk'in was a 260-day sacred calendar, 13 numbers combined with 20-day names. This created a cycle that repeated every 260 days. The Hab was a 365-day civil calendar, 18 months of 20 days each, plus 5 unlucky days at year's end. These 2 calendars synchronized every 52 years. This 52-year period was called the calendar round. It held profound religious significance for the Maya. But they also used a third system, the long count. This was an absolute time scale measuring days from a creation date. Most scholars believe the long count 0 date corresponds to August 11, 3114 BCE in our calendar. The long count used a modified Vigesimal system. The positions were kin, day, 1 Wienel, month, 20 kin-ton, year, 18 Wienel, 360 days, not 400. This was the only modification to pure base. 20 Katun, 20 Tun, 7,200 days. Baktun, 20 Katun, 144,000 days. A typical long count date looked like 9, 12, 11.5, and 18. Working from left to right, 9 Baktuns, 12 Katuns, 11 Tuns, 5 Wienels, 18 Kins. Calculating this gives a specific number of days since the creation date. This system could track dates millions of years into the future, and millions of years into the past. The Maya weren't just measuring time, they were conceptualizing it as mathematically infinite. Practical applications. Beyond astronomy. Maya mathematics wasn't purely theoretical. It had practical applications throughout their society. Trade and commerce depended on mathematical calculations. The Maya economy involved complex exchanges of goods: cacao beans, jade, textiles, pottery. Merchants needed to calculate quantities, values, and equivalencies. The Vigesimal system facilitated these transactions. Architecture and engineering required geometric calculations. Maya builders constructed massive pyramids with precise alignments. The Pyramid of Kukulkan at Chichen Itza demonstrates sophisticated understanding of geometry and proportion. During equinoxes, shadows create the illusion of a serpent descending the pyramid stairs. This required exact calculations of angles, heights, and solar positioning. Maya engineers built elaborate water management systems. The aqueduct at Palenque used advanced hydraulic engineering. Calculating water flow, pressure, and channel dimensions required mathematical knowledge. The Sakbi road network connected Maya cities across vast distances. These raised causeways stretched for miles through jungle and swamp. Surveying and constructing them required distance calculations and geometric precision. Some sackbees ran perfectly straight for dozens of miles. A remarkable engineering achievement requiring sophisticated mathematics. Why Europe lagged behind. So why was medieval Europe still struggling with Roman numerals while the Maya had developed such advanced mathematics centuries earlier? Roman numerals have fundamental limitations. They're additive and subtractive, not positional. 7 is 5 plus A1 plus A1. IV is 5, 1. This works fine for small numbers, but large numbers become unwieldy. Try multiplying MCMXLIV by DCCCXN using only Roman numerals. It's nearly impossible. Romans used abacuses for actual calculations, then recorded results in numerals. The numerals themselves weren't designed for computation. Medieval Europe inherited this system and stuck with it. Even after Arabic numerals, which actually originated in India, reached Europe around the 10th century CE, adoption was slow. Merchants resisted change. The Catholic Church was suspicious of pagan numbers. Universities debated whether Arabic numerals should be taught. It wasn't until the Renaissance that Arabic numerals became standard in Europe. Meanwhile, the Maya had been using zero and positional notation for over a millennium. The geographical disconnect meant Maya mathematical innovations never influenced Old World systems. But this makes their achievements even more remarkable. They developed these concepts independently, without any influence from Babylonian, Indian, or Chinese mathematics. Pure indigenous innovation. The legacy: rediscovering Maya mathematics. After the Spanish conquest in the 16th century, much Maya knowledge was destroyed. Spanish priests burned Maya books, considering them pagan. Only 4 codices survived. Hieroglyphic writing wasn't fully deciphered until the late 20th century. This meant centuries of Maya mathematical knowledge remained inaccessible. Today, scholars recognize the sophistication of Maya mathematics. Some schools in Mexico now teach Maya math alongside conventional mathematics. Students learn to count using dots, bars, and shells. This connects them to their cultural heritage, and it demonstrates that mathematical systems aren't universal. Different cultures develop different approaches. Modern mathematicians have also explored potential applications of base 20 systems. Some computer scientists suggest Vigesimal notation could be useful for certain programming applications. The efficiency of representing numbers with only 3 symbols has theoretical elegance. Most importantly, Maya mathematics reminds us that scientific and mathematical advancement isn't confined to one culture or region. Innovation happens independently across human societies. The Maya achieved mathematical sophistication that rivaled or exceeded contemporary civilizations in Europe, Asia, and Africa. Without contact, without borrowing, purely through their own intellectual development. Maya mathematics was extraordinary. A Vigesimal base 20 system requiring only 3 symbols. The independent invention of zero as both placeholder and number. Astronomical calculations accurate to within seconds per year. The ability to work with numbers in the hundreds of millions. Multiple interlocking calendar systems tracking cosmic cycles. All developed between 2000 BCE and 900 CE. While medieval Europe struggled with Roman numerals, the Maya were calculating Venus's synodic period to within hours of accuracy. While European merchants used abacuses because their number system couldn't handle multiplication, Maya traders used a positional notation system that made complex calculations straightforward. The Maya weren't just advanced for their time. In many ways, their mathematical system was more sophisticated than anything Europe would develop for another 1,000 years. This is a testament to human ingenuity across cultures, and a reminder that the history of mathematics is far richer and more diverse than we often recognize. If this changed how you see ancient mathematics, hit that like button. Subscribe for more discoveries about scientific achievements across different civilizations. Would you find it easier to learn mathematics using the Maya system, 3 symbols, base 20, or our current system, 10 symbols, base 10? Which system do you think is more intuitive, and why? Drop your thoughts in the comments below. We read every one and love discussing with you. Thanks for watching, and we'll see you next time.